In this video, we're going to have a look at balancing some of the more complicated redox half equations, where to put the electrons, what to do when there are things other than electrons to balance, and also looking at how we combine half equations to make ionic equations. So, balancing half equations. First of all, we're just going to look at some more straightforward ones. And one thing that's really important to note is that we need to balance the atoms first before we balance any electrons. So we can't always assume that the atoms are the same on each side. Looking at the first one, the atoms are the same, so there's one tin each side, there's no numbers in front. And looking at the charges, that's how I decide where to put the electrons. So we have tin with a 2+ charge on the left hand side and with a 4+ charge on the right. So to go from 2+ to 4+, I needed to lose 2 electrons. If I'm losing them, they're going on the product side. Other way to look at it is that if I add up 4+ and 2-, I will get 2+, which is the same as the total charge on the left. So I can use total charge for something simple like this, just to work it out. The charge doesn't have to be neutral on each side, it just needs to be the same on the left as it is on the right. In terms of the process that's happening here, this is oxidation. So I know it's oxidation because tin is losing electrons, because the oxidation number increases, so we go from 2+ to 4+, and the other way is simply just that the electrons are on the right hand side. So we can actually just use that as a shortcut to know that it's an oxidation reaction. Have a look at the next one, and the atoms are not balanced. So the first thing I needed to do was put a 2 in front of the Cl- so that it balanced out with the Cl2 on the left. So this is going to happen with all of these next ones because non-metals tend to be diatomic, which means that when they go from elements to ions or ions back to elements, we need to take that into account in our balancing. So chlorine has an oxidation number of 0 and chloride ion has an oxidation of -1, but there are 2 of them. So I'm going to need to add 2 electrons, 1 for each chlorine atom that is being reduced to -1. And it is reduction because we're going from 0 to -1. So probably the best way to learn whether something is oxidation or reduction is to use the change in oxidation number. Oxygen, 2 in front because it's making O2. This means I've got a total overall charge on the left hand side of 2 lots of -2. And I have no charge on the right hand side. So I'm going to add 4 electrons to balance that equation. Again, it's oxidation. We're going from -2 to 0 in oxygen, the element, so that is an increase in oxidation number. Again, we need to balance the atoms for hydrogen, so we have 2 lots of hydrogen ions, both with a +1 charge, going to 0 on the right. So to balance that with electrons, I need 2 electrons on the left-hand side, and that's going to be reduction because we're going from +1 in the hydrogen ion to 0 in hydrogen gas. So those are the ones without any complicated extra parts. These are the ones that people tend to get stuck on more. So the manganate ion is one of these ions we were talking about in the bonding topic. Is actually bonded to oxygen in the +7 state and then becomes manganese 2+ ions on the right without any oxygen. So the first thing is just to balance not all of the atoms, but just the manganese. So we're assuming that oxygen stays constant in these, and it will for most of them. So the oxidation number of oxygen won't change. We just need to make sure that the manganese is balanced, and in this case it is. There's 1 on the left and 1 on the right. So it's not Mn2O4 or anything else. We'll see another example later where that makes more sense. Now I obviously need to balance the oxygen atoms. So the thing about balancing oxygen is we can't use O2 to balance it, and the reason for that is because on the left hand side oxygen is in a -2 oxidation number. That's how we know that the manganese is +7. So oxygen is in a -2, and this is a half equation. Manganese is the one that is changing, not oxygen. So we can't include oxygen gas because then that suddenly has another aspect of another change in oxidation number. A half equation should only have one element that is being oxidized or reduced, and then normally oxygen, and as we'll see in a minute, hydrogen are the ones that will stay the same. So we're going to use H2O. In water, oxygen has a -2 oxidation state, so there's no change in oxidation number. And this is all happening in aqueous solution, so there's plenty of water around. And we can therefore use water on either side. Problem with this is we of course now generated some hydrogen on the right, which is not on the left. For the same reason, we need hydrogen in a +1 oxidation state because that's what it's in water. So we're going to use hydrogen ions. There is usually a clue in the question that these sorts of reactions are done in aqueous acidic solutions. So there is water present and there are hydrogen ions present. And in fact, that is why we have hydrogen ions present. So if you've done a titration with manganate, it's the purple chemical that turns very, very pale pink at the end of the reaction. It will be acidified manganate. If we use manganate as an oxidizing agent, it will have to be acidified for it to work. So I have now balanced almost everything, but of course it's a half equation, so the last thing I haven't balanced is the electrons. Now there are two ways of doing this. We're going to do it one way and then we're going to check it the other way. That's the beauty of there being two ways. The best way is to use oxidation numbers. So we can work out what the manganese is at the start, what it is on the right, and then look at the change in oxidation number that it undergoes in the reaction. Then we know how many electrons we should be adding and where. So if we add up my oxygens, oxygen has an oxidation number of -2. It's not in a particularly weird compound here. So 4 lots of -2 gives me -8. It's a bit hard to see, I've realised, but that is a -1 charge on the MnO4 ion. So we've got -8 from the oxygen. The whole thing adds up to -1. So the manganese must be +7, which is its maximum oxidation number because it's got 7 electrons in its 4s and 3d orbitals combined. On the right, much easier, it's just an ion, so its oxidation number is +2. So to go from +7 to +2, you have to -5. Each electron corresponds to -1, so I need to add 5 electrons on the left-hand side. So I've used oxidation numbers to work that out. Now what we're going to do is we're going to check the number of electrons is correct by adding up the total amount of charge on the left and the right, which is what we were doing for the more straightforward half equations. So looking on the left, I've got 5 minuses for my electrons, a 1 minus from the ions, that's 6 minus, plus 8 H pluses, which is +2. On the right, I've also got +2, so my charge is balanced. Another example, so we've got V2O5 on the left, V2 plus on the right. First thing I'm doing is I'm balancing the atoms. So because it's 2 lots of vanadium on the left, I'm going to need 2 lots of individual vanadium ions on the right hand side. So it's vanadium, the thing that is changing. The next thing I'm going to do is balance the oxygens using water, and there are 5 oxygens, so I'm going to need 5 waters on the right hand side. So my oxygen is now balanced. I've now generated some hydrogen on the right, which I need to balance with hydrogen ions. I need 10 hydrogen ions because I've got 5 lots of H2O. Last thing we do is check the electrons, and we're going to use oxidation numbers again. So oxygen is -2, there are 5 of them, so that's -10. This is not an ion, this is a neutral compound, so the 2 vanadiums each add up to +10, and I can leave it like that. If a question was asking me for the oxidation number of an individual vanadium atom, I would say it was +5. Or if a question simply said, what's the oxidation number of vanadium in the compound? Because there's 2 on the left and 2 on the right, I'm just going to leave it as +10 for now. So +10 on the left, there are 2 lots of +2 ions on the right hand side, so I do have to take that into account because I haven't divided my left by 2. So the overall change from a total of +10 to a total of +4 is -6, so I have to add 6 electrons. Let's now check the charge adds up. So on the left hand side, I've got 6 electrons, 6 minuses, and then I've got 10 pluses, and the V2O5 has nothing, so I've got a total of +4, and on the right I've got 2 lots of +2 ions, also a total of +4. So it all balances out fine and we can check. Another thing to notice about these sorts of reactions is that the hydrogen ions and the electrons always end up on the same side of the equation, and the water ends up on the opposite side. So in fact, when we talk about adding hydrogen as an example of reduction, this is really what we mean. You usually add hydrogen and you add electrons at the same time. So we've got a gain of electrons here. The vanadium is being reduced. The other way that I know that this is reduction is because we're going +10 to +4 or +5 to +2. Halides and halates. Okay, so halides and halates, what we mean is negative ions of halogens and negative ions of halogens containing oxygen. So imagine we had this question that says a balanced equation for reaction of iodate 5 ions and iodide ions to form iodine, and it says presence of sulfuric acid. So the first thing I need to work out is what is the formula of an iodate 5? You may be given it, but you could have to work it out. How would you do that? Well, I know it contains iodine and oxygen because we'll have the word iodate. I also know that 8 means a negative ion and that oxygen has a -2 oxidation number. So basically, if iodine has a +5 state, which is what's told in iodate 5, it's a case of how many oxygens do I need to add to my +5 until I get a negative charge. So if I just added 1 oxygen to a +5 iodine, that wouldn't work. That would give me a positive ion. So iodates are generally, and halate ions are negative. So it's really just how many oxygens I need to add, and I need to add 3 because 3 lots of -2 is -6. If I add that to my +5, I get a -1 charge. So the formula is IO3-. And there are lots of trends in this. Iodate 7 would be IO4-. You're just adding an oxygen and making it more positive by 2 each time. Iodide just means I-. Simple. That's what the "ide" means at the end. It means the negative ion of that atom. And then iodine means I2. That's what we always mean in chemistry when we talk about halogens on their own. Presence of sulfuric acid, I don't need to worry about the SO4 part, but it tells me that there is H+ ions present and that I can have H2O present as well because sulfuric acid must be dissolved in water. So initially, what can go wrong here is that we just go, oh, there's 2 iodines on the left and there's 2 on the right, so no problem. What you need to do in this is balance the change in oxidation numbers. This is not a half equation. This is a full, albeit an ionic equation, and that means that one of these substances is being oxidized and one is being reduced. So I need to write down the oxidation numbers at the top. We know iodine is +5 in iodate 5, clues in the name, -1 in the iodide, and there are 2 lots of 0, so the 2 atoms that have a 0 oxidation state in iodine. So right away we can see that this isn't balanced at all, even though the number of iodines appears balanced, because for IO3- to go to one of the iodines, so half a mole of I2, I'm going from +5 to 0, whereas in I minus, I'm going from -1 to 0. The amount of electrons lost is not the same as the amount of electrons gained. So I can kind of do a partial half equation to work it out. I need to add 5 electrons to my iodate 5 in order to get it to 0. But I only lose 1 electron every time an I minus ion changes to 0. So what do I need to do? Well, it's like a simultaneous equation. The electrons have to balance out. So I'm going to need 5 of my iodide ions so that they lose 5 electrons in total. And therefore my iodate ion can gain those 5 electrons. So actually my balancing is going to be a bit more complicated than just one of each. Now that I've balanced the oxidation numbers, everything else can be done the normal way. So balancing the atoms, I've now got more iodine atoms to add on. And then we go for balancing the oxygens using water. So I'm going to need 3 moles of water on the right. And then I'm going to need to add hydrogen ions because I've generated some hydrogen ions on the right. So I'm going to need 6 hydrogen ions. Don't forget, this is now a balanced equation. So this is a full equation showing redox and not half equation. So there don't need to be any electrons, but I can still check the charges balance because that still needs to be true of any equation. So on the left-hand side, I've got -1 from my IO3 minus. Don't get confused about the oxidation number of the iodine, which is +5, and the overall charge on the ion, which is -1. So -1 minus 5 is -6, +6. Add all of that up. There's 0 overall charge on the left, and there are 2 neutral molecules on the right, so there's 0 overall charge on the right, and I checked that it balances. That would never happen if I had not taken into account the oxidation numbers. I would never have been able to balance the charges. Watch out as well, all that happens if I want to change this for a different example. For example, if I had iodate 7, all that would happen is I'd have more oxygens, so it'd be IO4 minus, and I'd need 7 iodides. So if I had iodate 3, I would need 3 iodides because I'm going from 3 to 0, so I need 3 iodide ions to lose their electrons. And all the other numbers would change proportionally. Every time you have an extra oxygen in your iodate ion, you will need an extra water and an extra 2 hydrogens. So it all balances out. It's quite predictable. In fact, you could try writing equations for iodate 1, iodate 3, and iodate 7 with iodide, and you see they will come out the same way. This is not disproportionation, by the way, because we were starting with 2 elements in different oxidation states and ending up with 1 element in the same. This example we're now going to look at is disproportionation, which is a very similar thing in terms of using oxidation numbers to balance. So this time we're starting with bromine and we're making bromate 3 and bromide, but we haven't got hydrogen ions, we've got hydroxide ions. But we'll see how that works. So bromine is Br2. Working out bromate 3. So that means I'm actually going to need 2 oxygens to make my bromine have a +3 and overall have a -1 charge. Think about it, 2 lots of -2 is -4. Add that to my +3 and I've got a -1 charge on the ion overall. Bromide, Br-, as before. So as before, we are going to use, hydroxide ion also tells us that H2O is present, okay, because you can't have hydroxide ions unless you have an aqueous solution. So we're going to use oxidation numbers to balance this again. We are not just going to leap in and assume that there are 2 bromines on the right and therefore it's balanced. So oxidation numbers first. We've got 2 lots of 0 in our atoms on the left-hand side. We've got a +3 and a -1 on the right-hand side. So to get from 0 to +3, I need to gain 3 electrons, which means I need 3 bromide ions, 3 Br minuses. Each one's going to lose 1. So this is the same logic we applied before. To go from 5 to 0, you need 5 ions. It's just happening in a different direction, but the balancing idea is the same. Now what are we going to do? So this is slightly different. It's in the presence of hydroxide ions. So I'm actually not going to add water yet, and that's because hydroxide ions contain oxygen, and if I start adding water, I'm going to add more oxygen without knowing how many oxide ions. So the way of doing it with hydroxide ions is slightly different. So I've got negative charges on the right hand side and no negative charges on the left. In total, I've got a -1 from the bromate, and I've got 3 lots of -1 from my 3 bromides. So I've got 4 negative charges on the right. So I'm going to need 4 hydroxide ions on the left. Now what I do, so I'm not using H+ at any point because this is in the presence of an alkali, so there won't be H+ ions around. This is an alkali solution. Now I need to add it up. Well, I have 2 O's on the right and no H's, and on the left I've got 4 O's and 4 H's. So if I take away the 2 O's I've already got, that leaves me very conveniently with 4 hydrogens and 2 oxygens, which means I can balance the rest of it with H2O. So we use H2O last when we're doing an equation of disproportionation in halogens. So the order is different to other ones. My oxygen is balanced out. Again, if I needed more oxygens, so if it's bromate 5, I just have more Br minuses and I'd have more hydroxides and more waters. It goes up by the same amount each time. The reaction of halides with concentrated sulfuric acid is something that comes up a lot in redox topics as an example of a trend in the group's properties. So I thought I'd include it here in this video just while we're looking at changes in oxidation numbers and equations for those, and just link it to some of the observations that we would see during these reactions. You might want to check to see whether this is part of your A-level chemistry course, because it might be that it's not included in your syllabus. So halogen containing products, if you are adding concentrated sulfuric acid to the solid sodium halides, for example sodium fluoride and sodium chloride, then you will get hydrogen fluoride and hydrogen chloride respectively, and then the sulfur containing product will be HSO4 minus ion, so the hydrogen sulfate ion. So if I was balancing the equation, I would probably have sodium hydrogen sulfate as a product. That's if I started with sodium fluoride. So if I was doing the full equation, it would be NaF plus H2SO4 makes HF and NaHSO4. So what would I see during that reaction? Well, the hydrogen sulfate ion would just be with the sodium in a white compound. I wouldn't see that particularly, but I would see the formation of hydrogen fluoride and hydrogen chloride, and it's often described as steamy fumes, or sometimes misty fumes or white fumes, something like that. Try to avoid calling it smoke. Smoke is something very specific to incomplete combustion. And the reason I'd see those is, like, normally they're dissolved in water, but we're using concentrated, very concentrated sulfuric acid, so there's not much water there for those to dissolve in. And the important thing to note here in terms of redox is this is not a redox reaction. It is just an example of an acid-base reaction. It's a hydrogen ion being transferred from H2SO4 to the fluoride ion or the chloride ion. So it's simply a formation of a covalent bond between fluorine and chlorine and the hydrogen. So it's just transfer of H+, and it's not transferring both the hydrogen ions, because if you think about it, sodium fluoride and sodium chloride are not bases, they're just salts. So the only reason this hydrogen ion is transferred at all is because it's really concentrated sulfuric acid. So it's extreme conditions. And then we look at what would happen if I were to do the same with something like solid sodium bromide. So you're still going to make hydrogen bromide, so you're still going to see the steamy fumes. But you're also going to make bromine. So bromine is not a product of transferring a hydrogen. We've now got a change in oxidation number. So in hydrogen bromide, the bromine is still -1, as it was in sodium bromide, potassium bromide, whatever solid halide we started with. But with bromine, it's now in oxidation state 0. So that means something else must have happened to the sulfur. So I have made the hydrogen sulfate ion, but in this case, you would also make sulfur dioxide. In terms of what you would still see the steamy fumes for HBr. Bromine is obviously an extremely visible product, so all the halogens are coloured. You would get an orange or a reddy brown liquid, which could turn to vapour because it would be hot. It's a very exothermic reaction, and SO2 isn't really something you can see, but it has very choking fumes. It has a very nasty effect on the respiratory system. And then if we move to our iodide, then again, you're going to make hydrogen iodide. You're still going to see steamy fumes. You're going to make iodine. So there is still a redox change, and you're still likely to make SO2. So how is it different to bromide? Well, it's still making iodide, so that's the most oxidized that iodine is going to become in this reaction. It's not going to go more positive than 0. But what happens is more of the iodide ions are able to turn to iodine, and we're actually able to get more products from our sulfur. So as well as SO2, you're going to get sulfur on its own as an element, and you're also going to get hydrogen sulfide. So the observations here are going to be quite different. Iodine is a grey solid at room temperature, but this reaction is pretty warm, very exothermic, so it's likely you're going to see purple vapour. It's quite dramatic. Sulfur is a yellow solid, so you would see that formed at the end of the reaction. And then H2S is a gas, and you wouldn't see it, but it's the one that really everyone thinks of as sulfurous because it smells of eggs. So how is this different? Why have we got different products for bromine and iodine? It's to do with how much oxidation is going on, and therefore how much reduction is happening of the sulfur. So if we look at some oxidation numbers and see how this applies to the redox topic. Sulfuric acid, H2SO4, contains the sulfate ion with sulfur in the +6 oxidation state. We can work that out. Hydrogen is +1, oxygen is -2, so we've got +2, -8, sulfur must equal +6. That's the highest oxidation state of sulfur because it's in group 6 of the periodic table. And we've looked at the bonding of the sulfate ion at other places. Now, if you just take H+ away, you're leaving behind a minus charge, so you can do the maths and realise that in the hydrogen sulfate ion, the sulfur hasn't changed oxidation state, and my halogens haven't changed oxidation state either. They are still in the -1. They started as sodium fluoride, and now they're just hydrogen fluoride. So there's no change in oxidation state. Still fluoride, still 1-, just hydrogen ion transfer. And these are two separate reactions. When it comes to the bromine and the iodine, they're now going into 0 oxidation states. They've been oxidized, which means the sulfur must be reduced. If we look at SO2, oxygen has a -2 oxidation number, so the sulfur there must be +4. So we've gone from +6 to +4, and that is pretty much as far as the reaction will go with bromide. Then we look at the other products that you have with iodide. So we've still got sulfur dioxide +4. We're also going to make some sulfur, which has an oxidation state of 0. So we've now gone down even lower. We've gone from +6 to 0. And then my hydrogen sulfide, we've gone all the way down to -2. So in this case, sulfur is now bonded to hydrogen, and hydrogen is less electronegative than sulfur. So sulfur is now taking the negative oxidation state. It was taking a positive oxidation state before because it was bonded to oxygen. So we've actually seen the full range of sulfur's oxidation numbers in this reaction, from +6, which is the maximum it can be because of the group that it's in, to -2, which is the minimum it can be because 2 electrons is the most that it can gain, with 6 in the outer shell. And so what that is showing is the trend in how good the halide ions are at behaving as reducing agents. So fluoride and chloride are not behaving as reducing agents at all. They're simply accepting H+. So there's no redox happening when you put concentrated sulfuric acid with fluoride or chloride. But then with our bromide and our iodide, both of those are able to reduce sulfur from +6 to a lower oxidation number in the products. But bromide is only able to reduce sulfur to +4 and can't reduce it any lower, whereas iodide can produce sulfur and H2S. Now, you may see different things in different questions. Under certain conditions, maybe hotter or even more concentrated acids, sometimes bromide might be able to produce sulfur, but generally, the lower down the group we are going, the better they are as reducing agents, the ions. And that's the opposite to the trend as you go down the halogens as how good they are as oxidizing agents. So chlorine, the element, is very good at gaining electrons. This makes it a good oxidizing agent. It's a small atom which is able to attract electrons to its outer shell quite efficiently. That means that chloride is a poor reducing agent because it's not able to give its electrons back up as easily once it becomes a negative ion. Conversely, if we go to the bottom of the group, iodine is a very poor oxidizing agent because it's a very large atom with lots of shells, lots of shielding, so its ability to attract electrons towards it and take electrons away from another element is quite poor. But iodide, when it is in the form of a negative ion, is obviously therefore quite good at losing its electrons and being a reducing agent. So at the bottom of the group, you have stronger reducing agents as the halides. At the top of the group, you have stronger oxidizing agents as the halogens. If I was going to try and write any balanced equations for this, I would hope that I'd be given very clear ideas about what products I was going to make. So you wouldn't be guessing with bromide or iodide. You'd be told, given lots of clues as to what you'd make. If I was trying to balance it, I would write an equation for the hydrogen transfer separately to the equation for the redox. And then if I needed to, I would put those two equations together, but that would be pretty challenging and unlikely to come up very often.